Lesson Introduction. Secure protocol and application development concepts are essential pillars of robust cybersecurity. Protocols such as HTTPS, SMTPS, and SFTP provide encrypted communication channels, ensuring data confidentiality and integrity during transmission. Similarly, email security protocols like SPF, DKIM, and MARC work to authenticate sender identities and safeguard against phishing and spam. Secure coding practices encompass input validation to thwart attacks like SQL injection or XSS, enforcing the principle of least privilege to minimize exposure during a breach, implementing secure session management, and consistently updating and patching software components. Developers must also design software that generates structured, secure logs to support effective monitoring and alerting capabilities. Lesson objectives. In this lesson, you will do the following. Understand secure protocol concepts. Explore DNS filtering capabilities. Review email security protocols. Explore application security techniques. Review sandboxing concepts. Rate your confidence.
Continue. Category.
Topic 11A. Application Protocol Security Baselines. Report content errors. Copyright CompTIA A. Exam objectives covered. 4.5 Given a scenario, modify enterprise capabilities to enhance security. Secure protocols are fundamental in maintaining the security of data. Secure protocols include HTTPS, Hypertext Transfer Protocol Secure, for secure web traffic, SMTPS and IMAPs for securing traditional email protocols, SFTP, SSH File Transfer Protocol, or FTPS, File Transfer Protocol Secure, LDAPs for secure directory access, and DNSSEC for secure DNS queries. These protocols ensure that sensitive data is transmitted securely. Additionally, several protocols exist to help identify and mitigate phishing and spam emails by authenticating sender identities and checking message integrity, including protocols such as SPF, Sender Policy Framework, DKIM, Domain Keys Identified Mail, and MARC, Domain-Based Message Authentication, Reporting and Conformance. These protocols establish trust in email communications, reducing the likelihood of successful phishing and spam attacks.
Continue. Continue.
Secure protocols. Many of the protocols used on computer networks today were developed many decades ago when functionality was paramount, trustworthiness was assumed instead of earned, and network security was less of an issue than it is today. Many early-era protocols have secure alternatives or can be configured to incorporate security features, whereas others must simply be avoided. Insecure protocols, such as HTTP and Telnet, transmit data in clear text format, meaning anyone accessing the data packets can read any intercepted data sent over a network. In contrast, secure protocols like HTTPS and SSH, as alternatives to HTTP and Telnet, use encryption to protect transmitted data and improve security. Using HTTPS is crucial for protecting sensitive user information, such as login credentials and data entered into form fields, from being stolen when using web pages. System and network engineers must use SSH instead of Telnet when connecting to servers and equipment to ensure their login information, data, and commands are encrypted. Unfortunately, secure protocols are typically more complex to implement, manage, and maintain when compared to their insecure counterparts, and so are often avoided or disabled. For example, HTTPS requires obtaining a valid SSL/TLS certificate from a certificate authority, CA. After obtaining the appropriate certificate, it must be correctly installed and configured on a server, which requires more skill, time, and planning than simply enabling and using HTTP. Secure protocols leverage encryption and decryption, which require the correct handling of cryptographic keys, including processes regarding how they are created, stored, distributed, and revoked. Additionally, after properly obtaining and configuring the certificate, it must be managed effectively to ensure it remains trustworthy and does not expire. Troubleshooting issues with secure protocols is more challenging compared to insecure counterparts because administrators cannot easily inspect the content of data packets when troubleshooting issues, and the configuration of secure software and operating systems is more complicated and prone to misconfiguration compared to simple configurations that use insecure protocols. Despite these complexities, the security benefits provided by secure protocols significantly outweigh the challenges. All protocols should be secure unless specific justifications warrant using insecure ones. Implementing secure protocols. Organizations usually follow formal processes when selecting secure protocols to ensure comprehensive documentation and well-informed decision-making. These processes include assessing risks, reviewing policies, and evaluating the security features of different protocols. Organizations may also consult with technical experts or vendors for recommendations. The outcomes of these processes are documented, which is useful for audits and compliance reviews. Additionally, these process outcomes will typically impact security baselines and configuration management systems. Selecting protocols, assigning ports, setting transport methods, and other security considerations require careful consideration. The first step requires evaluating the data type used and its sensitivity level. Organizations should select secure protocols like HTTPS, SSH, and SFTP/FTPS for transmitting sensitive or private data. Configuring TCP ports depends on the protocol, as standard ports are associated with specific protocols. HTTP commonly uses port 80, HTTPS uses port 443. While default protocol ports can be changed, doing so may complicate configuration and cause potential accessibility issues. However, many administrators choose to change standard default ports and a method to obscure them. TCP, Transmission Control Protocol, and UDP, User Datagram Protocol, are two principal transport methods. TCP is connection-oriented and provides reliability, ordering, and error checking, making it suitable for applications requiring high levels of reliability. UDP is connectionless, making it faster than TCP and more suitable for real-time applications like video streaming, telephony, and gaming, where occasional packet loss is less impactful. When selecting secure protocols, administrators and analysts must consider suitable encryption levels, authentication methods, existing firewalls or other security equipment, and other factors which may impact the operation of the systems and software they are intended to protect. Ultimately, protocol selection requires an optimum balance among security, maintainability, performance, and cost. Rate your confidence. Transport layer security. As with other early TCP/IP application protocols, HTTP communications are not secured. Secure Sockets Layer (SSL) was developed by Netscape in the 1990s to address the lack of security in HTTP. SSL proved very popular with the industry and was quickly adopted as a standard named Transport Layer Security (TLS). It is typically used with the HTTP application, referred to as HTTPS or HTTP Secure, but can also be used to secure other application protocols and as a virtual private networking (VPN) solution. To implement TLS, a server is assigned a digital certificate signed by some trusted certificate authority (CA). The certificate proves the server's identity, assuming that the client trusts the CA, and validates the server's public/private key pair. The server uses its key pair and the TLS protocol to agree on mutually supported ciphers with the client and negotiate an encrypted communication session. HTTPS operates over port 443 by default. HTTPS operation is indicated by using https:// for the URL and by a padlock icon shown in the browser. It is also possible to install a certificate on the client so that the server can trust the client. This is not often used on the web, but is a feature of VPNs and enterprise networks that require mutual authentication. SSL/TLS versions. While the acronym SSL is still used, the transport layer security versions are the only ones that are safe to use. A server can provide support for legacy clients, but obviously this is less secure. For example, a TLS 1.2 server could be configured to allow clients to downgrade to TLS 1.1 or 1.0, or even SSL 3.0 if they do not support TLS 1.2. A downgrade attack is where an on-path attack tries to force the use of a weak cipher suite and SSL/TLS version. TLS version 1.3 was approved in 2018. One of the main features of TLS 1.3 is removing the ability to perform downgrade attacks by preventing the use of unsecure features and algorithms from previous versions. There are also changes to the handshake protocol to reduce the number of messages and speed up connections. Cipher suites. A cipher suite is the algorithm supported by both the client and server to perform the different encryption and hashing operations required by the protocol. Prior to TLS 1.3, a cipher suite would be written in the following form: ECDHE, RSA, AES 128, GCM, SHA 256. This means that the server can use elliptic curve Diffie-Hellman ephemeral mode for session key agreement, RSA signatures, 128-bit AES GCM, Galois counter mode for symmetric bulk encryption, and 256-bit SHA for HMAC functions. Suites the server prefers are listed earlier in its supported cipher list. TLS 1.3 uses simplified and shortened suites. A typical TLS 1.3 cipher suite appears as follows: TLS_ES_256_GCM_SHA 384. Only ephemeral key agreement is supported in 1.3 and the signature type is supplied in the certificate, so the cipher suite only lists the bulk encryption key strength and mode of operation, AES_256_GCM, plus the cryptographic hash algorithm, SHA 384, used within the new hash key derivation function, HKDF. HKDF is the mechanism by which the shared secret established by DH key agreement is used to derive symmetric session keys. Viewing the TLS handshake in a Wireshark packet capture. Note that the connection is using TLS 1.3 and one of the shortened cipher suites, TLS_AES_128_GCM_SHA 256. Secure directory services. A network directory lists the subjects, principally users, computers and services, and objects, such as directories and files, available on the network plus the permissions that subjects have over objects. A directory facilitates authentication and authorization, and it is critical that it be maintained as a highly secure service. Most directory services are based on the Lightweight Directory Access Protocol, LDAP, running over port 389. The basic protocol provides no security and all transmissions are in plaintext, making it vulnerable to sniffing and on-path attacks. Authentication, referred to as binding to the server, can be implemented in the following ways. No authentication means anonymous access is granted to the directory. Simple bind means the client must supply its distinguished name, DN, and password, but these are passed as plaintext. Simple authentication and security layer, SASL, means the client and server negotiate the use of a supported authentication mechanism, such as Kerberos. The startles command can be used to require encryption, sealing, and message integrity signing. This is the preferred mechanism for Microsoft's Active Directory, AD, implementation of LDAP. LDAP Secure, LDAPS, means the server is installed with a digital certificate, which it uses to set up a secure tunnel for the user credential exchange. LDAPS uses port 636. If secure access is required, anonymous and simple authentication access methods should be disabled on the server. Generally, 2 levels of access will need to be granted on the directory: read-only access, query, and read/write. Unless hosting a public service, the LDAP directory server should only be accessible from the private network. This means that the LDAP port should be blocked by a firewall from access over the public interface. If there is integration with other services over the internet, ideally only authorized IPs should be permitted. Simple Network Management Protocol Security. The Simple Network Management Protocol, SNMP, is a widely used framework for management and monitoring. SNMP consists of an SNMP monitor and agents. The agent is a process, software, or firmware running on a switch, router, server, or other SNMP-compatible network device. This agent maintains a database called a Management Information Base, MIB, that holds statistics relating to the activity of the device. For example, the number of frames per second handled by a switch. The agent is also capable of initiating a trap operation where it informs the management system of a notable event, port failure, for instance. The threshold for triggering traps can be set for each value. Device queries take place over port 161 UDP. Traps are communicated over port 162, also UDP. The SNMP monitor, a software program, provides a location from which network activity can be overseen. It monitors all agents by polling them at regular intervals for information from their MIBs and displays the information for review. It also displays any trap operations as alerts for the network administrator to assess and act upon as necessary. If SNMP is not used, it should be disabled. When running SNMP, the following includes some important guidelines. SNMP community names are sent in plain text, and so should not be transmitted over the network if there is any risk that they could be intercepted. Use difficult-to-guess community names. Never leave the community name blank or set to the default. Use access control lists to restrict management operations to known hosts, that is, restrict to 1 or 2 host IP addresses. Use SNMP v3 whenever possible and disable older versions of SNMP. SNMP v3 supports encryption and strong user-based authentication. Instead of community names, the agents are configured with a list of usernames and access permissions. When authentication is required, SNMP messages are signed with a hash of the user's passphrase. The agent can verify the signature and authenticate the user using its own record of the passphrase. File transfer services. There are many ways of transferring files across networks. A network operating system can host shared folders and files, enabling them to be copied or accessed over the local network or via remote access, over a VPN, for instance. Email and messaging apps can send files as attachments. HTTP supports file download and uploads via various scripting mechanisms. There are also peer-to-peer file sharing services. Despite the availability of these newer protocols and services, the File Transfer Protocol, FTP, remains very popular because it is efficient and has wide cross-platform support. File Transfer Protocol. A File Transfer Protocol, FTP, server is typically configured with several public directories. Transfer Protocol. A File Transfer Protocol, FTP, server is typically configured with several public directories, hosting files, and user accounts. Most HTTP servers also function as FTP servers, and FTP services, accounts, and directories may be installed and enabled by default when you install a web server. FTP is more efficient than file attachments or HTTP file transfer, but has no security mechanisms. All authentication and data transfer are communicated as plaintext, meaning that credentials are easily picked out of intercepted FTP traffic. You should check that users do not install unauthorized servers on their PCs, a rogue server. For example, a version of IIS that includes HTTP, FTP, and SMTP servers is shipped with client versions of Windows, though it is not installed by default. SSH-FTP, SFTP, and FTP over SSL, FTPS. Secure File Transfer Protocol, SFTP, addresses privacy and integrity issues of FTP by encrypting the authentication and data transfer between client and server. In SFTP, a secure link is created between the client and server using Secure Shell, SSH, over TCP port 22. Ordinary FTP commands and data transfer can then be sent over the secure link without the risk of eavesdropping or on-path attacks. This solution requires an SSH server that supports SFTP and SFTP client software. Another means of securing FTP is to use the Connection Security Protocol SSL/TLS. There are two means of doing this. Explicit TLS, FTPS, uses the AUTH-TLS command to upgrade an unsecure connection established over port 21 to a secure one. This protects authentication credentials. The data connection for the file transfers can also be encrypted using the proc command. Implicit TLS, FTPS, negotiates an SSL/TLS tunnel before the exchange of any FTP commands. This mode uses the secure port 990 for the control connection. FTPS is tricky to configure when there are firewalls between the client and server. Consequently, FTPS is usually the preferred method. Email services. Email services use two types of protocols. The Simple Mail Transfer Protocol, SMTP, specifies how mail is sent from one system to another. A mailbox protocol stores messages for users and allows them to download them to client computers or manage them on the server. Secure SMTP, SMTPS. To deliver a message, the SMTP server of the sender discovers the IP address of the recipient SMTP server using the domain name part of the email address. The SMTP server for the domain is registered in DNS using a mail exchanger, MX, record. SMTP communications can be secured using TLS. This works much like HTTPS with a certificate on the SMTP server. There are two ways for SMTP to use TLS. Startles is a command that upgrades an existing unsecure connection to use TLS. This is also referred to as explicit TLS or opportunistic TLS. SMTPS establishes the secure connection before any SMTP commands, hello, for instance, are exchanged. This is also referred to as implicit TLS. The Startles method is generally more widely implemented than SMTPS. Typical SMTP configurations use the following ports and secure services. Port 25 is used for message relay between SMTP servers or message transfer agents, MTA. If security is required and supported by both servers, the Startles command can be used to set up the secure connection. Port 587 is used by mail clients, message submission agents, MSA, to submit messages for delivery by an SMTP server. Servers configured to support port 587 should use Startles and require authentication before message submission. Port 465 is used by some providers and mail clients for message submission over implicit TLS, SMTPS, though this usage is now deprecated by standards documentation. Secure POP, POP3S. The Post Office Protocol v3, POP3, is a mailbox protocol designed to store the messages delivered by SMTP on a server. When the client connects to the mailbox, POP3 downloads the messages to the recipient's email client. Configuring mailbox access protocols on a server. A POP3 client application, such as Microsoft Outlook or Mozilla Thunderbird, establishes a TCP connection to the POP3 server over port 110. The user is authenticated by username and password, and the contents of their mailbox are downloaded for processing on the local PC. POP3S is the secured version of the protocol operating over TCP port 995 by default. Secure IMAP, IMAPs. Compared to POP3, the Internet Message Access Protocol, IMAP, supports permanent connections to a server and connects multiple clients to the same mailbox simultaneously. It also allows a client to manage mail folders on the server. Clients connect to IMAP over TCP port 143. They authenticate themselves, then retrieve messages from the designated folders. Like other email protocols, the connection can be secured by establishing an SSL/TLS tunnel. The default port for IMAPs is TCP port 993. Email security. Three technologies have emerged as essential for verifying the authenticity of emails and preventing phishing and spam: Sender Policy Framework, SPF, Domain Keys Identified Mail, DKIM, and domain-based message authentication, reporting and conformance, DMARC. Sender Policy Framework, SPF, is an email authentication method that helps detect and prevent sender address forgery commonly used in phishing and spam emails. SPF works by verifying the sender's IP address against a list of authorized sending IP addresses published in the DNS-TXT records of the email sender's domain. When an email is received, the receiving mail server checks the SPF record of the sender's domain to verify the email originated from one of the pre-authorized systems. Displaying the TXT records for Microsoft, using the DIG tool. Screenshot used with permission from Microsoft. Domain Keys Identified Mail, DKM, leverages encryption features to enable email verification by allowing the sender to sign emails using a digital signature. The receiving email server uses a DKTM record in the sender's DNS record to verify the signature and the email's integrity. Domain-based message authentication, reporting and conformance, DMARC, uses the results of SPF and DKIM checks to define rules for handling messages, such as moving messages to quarantine or spam, rejecting them outright, or tagging the message. DMARC also provides reporting capabilities, giving the owner of a domain visibility into which systems are sending emails on their behalf, including unauthorized activity. Performing a DMARC lookup using the DNS checker website https://dnchecker.org. The combined use of SPF, DKIM, and DMARC significantly enhances email security by making it much more difficult for attackers to impersonate trusted domains, which is one of the most common tactics used in phishing and spam attacks. These protocols are essential tools in the fight against email-based threats because they provide essential mechanisms that help verify the authenticity of emails, maintain the integrity of the email content, and ensure the safe delivery of electronic communication. Email Gateway. An email gateway is the control point for all incoming and outgoing email traffic. It acts as a gatekeeper, scrutinizing all emails to remove potential threats before they reach inboxes. Email gateways utilize several security measures, including anti-spam filters, antivirus scanners, and sophisticated threat detection algorithms to identify phishing attempts, malicious URLs, and harmful attachments. Email gateways leverage DMARC, SPF, and DKIM to automate the authentication and validation of email senders, reducing the chances that spoofed or impersonated emails will be delivered. Email gateways also play a critical role in policy enforcement by allowing organizations to create rules related to email content and attachments based on established policies or regulatory compliance requirements. Attachment blocking, content filtering, and data loss prevention are common tasks email gateways handle. Secure/multipurpose Internet Mail Extensions. Secure/multipurpose Internet Mail Extensions, S/MIME, is a protocol for securing email communications. It encrypts emails and enables sender authentication to ensure the confidentiality and integrity of email communications. S/MIME uses public key encryption techniques to secure email content, the body of email. S/MIME also incorporates digital signatures to support sender verification and ensure messages are unmodified. By providing encryption and authentication capabilities, S/MIME significantly enhances the security of email communication, but its implementation is often complicated and prone to misconfiguration. Rate your confidence.
In this demonstration, we'll discuss how to prevent spam being relayed off of your email servers. To do this, we've installed an SMTP email service on this Windows Server 2016 system. Let's go to Tools. We're going to go to the IIS 6.0 Manager. Expand that. Okay, we manage this service using the IIS Manager 6.0. Most email servers currently available will have similar SMTP capabilities and provide the same SMTP options. Firstly, we can right-click on our SMTP server, go to Properties, and from here we can lock down this email server. We're going to go to the Access tab. On the Access tab, you can require authentication to access this server. The default is anonymous access, meaning anybody can connect without authenticating. You should disable this option and require at least basic authentication. If you have anonymous authentication enabled, and if you allow Open Relay, spammers will quickly find this system and start bouncing spam off your server to cover their tracks. If this happens, you are the one who gets in trouble, and your ISP may block or blacklist your email server. You can also use integrated Windows authentication, which would require you to use the domain credentials to authenticate. Basic authentication requires users just to enter a password, but beware that basic authentication is sent clear text by default, which would expose the password. Alternatively, you can also combine it with TLS encryption, which is the next generation of SSL, basically to secure authentication credentials as they are transmitted on the network. You can also require a secure connection to connect to this MTP server in the first place. This option requires an SSL or TLS certificate for this server to secure the connection. You can also use connection controls to configure who's allowed to connect to this SMTP server and who is blocked from connecting. This can be done using your IP addresses. You can use a range of IPs. You can also do this using domain names as well. This requires reverse DNS lookups to be enabled. Using this information, you can restrict who is allowed access to the server. You can also implement relay restrictions, which are used to specify who is allowed to relay email through the SMTP server. You can allow everyone except for those specified on the list, or block everyone except for those on the list. As before, you can also specify an IP or IP range or domain name. That's it for this demonstration. In this demonstration, we reviewed several security configurations you can implement to prevent email from being relayed off of your SMTP server.
Email data loss prevention. Email is one of the most frequently used communication channels within organizations. It serves as a conduit for sensitive data such as financial information, intellectual property, customer and employee data, and personally identifiable information, PI. Given its popularity and the sensitivity of the data it often carries, email is a common vector for data loss, making data loss prevention, DLP, protections exceedingly important. While convenient, the ease of use and quick transmission capabilities of email can inadvertently encourage careless handling of sensitive data. Human errors, such as sending confidential data to the wrong recipients or failing to use secure methods for data transmission, are common and underscore the importance of DLP measures. In addition, DLP solutions are crucial in guarding against insider threats. Insiders can pose significant data leakage risks due to a lack of policy awareness or malicious intent. Regulations like GDPR, HIPAA, and PCI DSS impose stringent requirements for protecting specific data types, with DLP serving as a key mechanism to ensure compliance and avoid unauthorized data transmission. Additionally, because email is a primary target for attacks, DLP protections significantly mitigate the risk of data loss, ensuring the appropriate handling and protection of sensitive information. Data loss prevention, DLP, technologies prevent unauthorized sharing or dissemination of sensitive information. DLP policies are essential for monitoring and controlling the content used in communication platforms like email. DLP scans emails and attachments for certain types of sensitive information defined by the organization's DLP policies, including credit card numbers, social security numbers, proprietary information, or any sensitive or confidential data. If an email contains these types of information, the DLP system can take several actions based on predefined rules, such as blocking the email, alerting the sender or administrator, or automatically encrypting it before transmission. Enforcing DLP in email is essential for many organizations, especially those handling sensitive customer data or subject to regulations like GDPR, HIPAA, or PCI DSS. DLP helps organizations minimize the risk of data breaches, avoid noncompliance penalties, and maintain data security and privacy. DLP is often enforced using email gateways and security policies on endpoint protection tools. Rate DNS filtering. Domain name system, DNS. Filtering is a technique that blocks or allows access to specific websites by controlling the resolution of domain names into IP addresses. It operates on the principle that for a device to access a website, it must first resolve its domain name into its associated IP address, a process managed by DNS. When a request is made to resolve a website URL, the DNS filter checks the request against a database of domain names. If the domain is associated with malicious activities or is on an unapproved list for any reason, the filter blocks the request, preventing access to the potentially harmful website. DNS filtering is highly effective for many reasons. A few are listed below. It provides a proactive defense mechanism, blocking access to known phishing sites, malware distribution sites, and other malicious online destinations. It can help enforce an organization's acceptable use policies, AUPs, by blocking access to inappropriate or distracting websites and ensuring that the internet is used responsibly and productively. It can protect all devices connected to a network, including IoT devices, providing an extra layer of security. It is a simple solution that is easy to implement and presents minimal risk, making it a cost-effective security control suitable for networks of any size. While DNS filtering is highly effective, it must be combined with other security measures for comprehensive protection. Implementing DNS filtering. DNS filtering is implemented using different methods and tools. A prevalent method is through DNS filtering services like Cisco's OpenDNS, https://www.opendns.com, Quad9, https://www.quad9.net, or clean browsing, https://cleanbrowsing.org. These services provide DNS resolution with built-in filtering, simply requiring organizations and users to redirect their DNS requests to the filtering service's DNS servers. Organizations that manage their own DNS servers, such as Microsoft's DNS Server or Bind, can directly implement DNS filtering. This method, albeit more complex, provides complete control over filtering policies and permits the integration of block lists or response policy zone, RPZ, feeds into server configurations. Another strategy involves using DNS firewalls, which intercept DNS queries at the network level and apply filtering rules accordingly. Some endpoint protection tools and antivirus software provide DNS filtering capabilities to provide device-level protection ideal for laptops and other mobile devices that may connect to numerous networks with varying levels of security enabled by default. Open source Pi-hole, https://pi-hole.net, or AdGuard, https://github.com/adguard-team/adguard-home. Software can be configured as a local DNS resolver with filtering capabilities. This software runs on Linux and is commonly implemented using Raspberry Pi hardware due to its low performance overhead. Regardless of the method chosen, customization of filtering policies allows for categorizing websites to simplify the creation of block lists or allow lists per requirements. Keeping DNS filters updated is essential to effective DNS filtering to keep pace with evolving threats and changing organizational needs.
Description.
Status is displayed at the top left. Dashboard option is selected from the options in the left pane. The dashboard displays total queries, 5 clients, 3,416, queries blocked, 491% blocked, 14.4%, and domains on block list, 82,309. 2 vertical bar graphs are titled total queries over last 24 hours and client activity over last 24 hours. Can directly implement DNS filtering. This method, albeit more complex, provides complete control over filtering policies and permits the integration of block lists or response policy zone, RPZ, feeds into server configurations. Another strategy involves using DNS firewalls, which intercept DNS queries at the network level and apply filtering rules accordingly. Some endpoint protection tools and antivirus software provide DNS filtering capabilities to provide device-level protection ideal for laptops and other mobile devices that may connect to numerous networks with varying levels of security enabled by default. Open source Pi-hole, https://pi-hole.net, or AdGuard, https://github.com/adguardteam/adguardhome. Software can be configured as a local DNS resolver with filtering capabilities. This software runs on Linux and is commonly implemented using Raspberry Pi hardware due to its low performance overhead. Regardless of the method chosen, customization of filtering policies allows for categorizing websites to simplify the creation of block lists or allow lists per requirements. Keeping DNS filters updated is essential to effective DNS filtering to keep pace with evolving threats and changing organizational needs.
Description.
Status is displayed at the top left. Dashboard option is selected from the options in the left pane. The dashboard displays total queries, 5 clients, 3,416, queries blocked, 491% blocked, 14.4%, and domains on block list, 82,309. Two vertical bar graphs are title total queries over last 24 hours and client activity over last 24 hours. The Pi-hole administrative dashboard showing DNS resolution statistics. Screenshot courtesy of Pi-hole. DNS security. DNS is a critical service that should be configured to be fault-tolerant. DOS attacks are hard to perform against the servers that perform internet name resolution, but if an attacker can target the DNS server on a private network, it is possible to seriously disrupt the operation of that network. To ensure DNS security on a private network, local DNS servers should only accept recursive queries from local hosts, preferably authenticated local hosts, and not from the internet. You also need to implement access control measures on the server to prevent a malicious user from altering records manually. Similarly, clients should be restricted to using authorized resolvers to perform name resolution. Attacks on DNS may also target the server application and/or configuration. Many DNS services run on Bind, Berkeley Internet Name Domain, distributed by the Internet Systems Consortium, ISC.org. There are known vulnerabilities in many versions of the Bind server, so it is critical to patch the server to the latest version. The same general advice applies to other DNS server software, such as Microsoft's. Obtain and check security announcements and then test and apply critical and security-related patches and upgrades. DNS footprinting means obtaining information about a private network by using its DNS server to perform a zone transfer, all the records in a domain, to a rogue DNS or simply by querying the DNS service, using a tool such as InSlookup or DIG. To prevent this, you can apply an access control list to prevent zone transfers to unauthorized hosts or domains, to prevent an external server from obtaining information about the private network architecture. DNS security extensions, DNSSEC, help to mitigate against spoofing and poisoning attacks by providing a validation process for DNS responses. With DNSSEC enabled, the authoritative server for the zone creates a package of resource records called an RSET signed with a private key, the zone signing key. When another server requests a secure record exchange, the authoritative server returns the package along with its public key, which can be used to verify the signature. The public zone signing key is itself signed with a separate key signing key. Separate keys are used so that if there is some sort of compromise of the zone signing key, the domain can continue to operate securely by revoking the compromised key and issuing a new one. Description. The tabs at the top are File, Action, View, and Help. The option Classroom.local under the folder Forward Lookup Zones folder is selected from the left pane. The right pane shows a table that lists the name, type, data, and timestamp. Windows Server DNS services with DNSSEC enabled. Screenshot used with permission from Microsoft. The key signing key for a particular domain is validated by the parent domain or host ISP. The top-level domain trusts are validated by the regional internet registries, and the DNS root servers are self-validated, using a type of MFN control group key signing. This establishes a chain of trust from the root servers down to any particular subdomain. Rate your objectives covered. 4.1 Given a scenario, apply common security techniques to computing resources. Cloud and web application security include cloud hardening, which fortifies cloud infrastructure and reduces its attack surface, and application security, which ensures software is securely designed, developed, and deployed. Both practices work together to establish a layered defense strategy, effectively protecting against many different threats. Secure coding practices include input validation techniques, incorporating the principle of least privilege, maintaining secure session management, enforcing encryption, patching support, and many other capabilities. Additionally, developers must design software that produces comprehensive, structured, and meaningful logs while incorporating real-time alerting mechanisms. These complementary practices support a safe and secure cloud and web application environment.
Secure coding technique.
The security considerations for new programming technologies should be well understood and tested before deployment. One of the challenges of application development is that the pressure to release a solution often trumps any requirement to ensure that the application is secure. A legacy software design process might be heavily focused on highly visible elements such as functionality, performance, and cost. Modern development practices use a security development lifecycle running in parallel or integrated with a focus on software functionality and usability. Examples include Microsoft's SDL, Microsoft com/and-us/security engineering/SDL, and the OWASP Software Assurance Maturity Model, OWASP, org/www-project-SAMM, and Security Knowledge Framework, https://OWASP, org/project/spotlight/historical/2021-0203. OWASP also collates descriptions of specific vulnerabilities, exploits, and mitigation techniques, such as the OWASP Top 10, OWASP, org/www-project-top-10. Input validation. Input validation is an essential protection technique used in software and web development that addresses the issue of untrusted input. Untrusted input describes how an attacker can provide specially crafted data to an application to manipulate its behavior. Injection attacks exploit the input mechanisms applications rely on to execute malicious commands and scripts to access sensitive data, control the operation of the application, gain access to otherwise protected backend systems, and disrupt operations. OWASP provides an excellent overview of input validation at https://cheatsheets OWASP org/cheatsheets/input_validation_cheat_sheet HTML. Without effective input validation, applications are vulnerable to many different classes of injection attacks, such as SQL injection, code injection, cross-site scripting, XSS, and many others. Validation method.
Description.
Allow listing. This method only permits inputs that match a predetermined and approved set of values or patterns. Block listing. This approach explicitly blocks known harmful inputs, such as certain special characters or patterns commonly used in attacks. Data type checks. These checks ensure the input data is of the expected type, such as a string, integer, or date. Range checks. These validate that numeric inputs fall within expected ranges. Regular expressions. Also known as regex, these are used to match input to expected patterns or signs of malicious activity. Encoding. This helps to safely and reliably prevent special characters and input from being interpreted as executable commands or scripts. Secure cookies. Cookies are small pieces of data stored on a computer by a web browser while accessing a website. They maintain session states, remember user preferences, and track user behavior and other settings. Cookies can be exploited if not properly secured, leading to attacks such as session hijacking or cross-site scripting. To implement secure cookies, developers must follow certain well-documented principles, such as using the secure attribute for all cookies to ensure they are only sent over HTTPS connections and protected from interception via eavesdropping, using the HTTP only attribute to prevent client-side scripts from accessing cookies and protect against cross-site scripting attacks, and using the same site attribute to limit when cookies are sent to mitigate cross-site request forgery attacks. Additionally, cookies should have expiration time limits to restrict their usable life. Secure cookie techniques are critical in mitigating several web-based application attacks, particularly those focused on unauthorized access or manipulation of session cookies. Developers can defend against attacks that target them by employing specific attributes within cookies. Static code analysis. Static code analysis is a crucial software development practice. It involves scrutinizing source code to identify potential vulnerabilities, errors, and non-compliant coding practices before the program is finalized. By examining code in a static state, developers can catch and rectify issues early in the development lifecycle, making it a proactive approach to building secure, reliable, and high-quality software. Application security approaches focus on software development and deployment lifecycles, with a heavy emphasis on secure coding practices that encourage developers to write code that prevents common vulnerabilities like SQL injection and cross-site scripting. Application security practices also mandate static application security testing, SCST, and dynamic application security testing, DST. Coding practices designed to support regular patching and updates are crucial to support the prompt resolution of newly discovered vulnerabilities. Static code analysis supports secure coding and is performed using specialized tools, often integrated into software development suites. These tools automate code checks against predetermined rules and flag potential issues so developers can review and address them. Some commonly used static analysis tools include SonarCube, https://www sonarzourc.com/products/sonarcube, Coverity, https://www synopsys.com/software-integrity/security-testing/static-analysis-SAST, HTML, and Fortify, https://www opentext.com/products/fortify-static-code-analyzer. Code signing practices use digital signatures to verify the integrity and authenticity of software code. Code signing serves a dual purpose, ensuring that software has not been tampered with since signing and confirming the software publisher's identity. When software is digitally signed, the signer uses a private key to encrypt a hash or digest of the code. This encrypted hash and the signer's identity form the digital signature. Code signing requires using a certificate issued by a Trusted Certificate Authority, CA. The certificate contains information about the signer's identity and is critical for verifying the digital signature. If the certificate is valid and issued by a trusted CA, the software publisher's identity can be confidently verified. Code signing helps analysts and administrators block untrusted software and also helps protect software publishers by providing a mechanism to validate the authenticity of their code. Overall, code signing helps build trust in the software distribution process. While code signing provides assurance about the origin of code and verifies code integrity, it does not inherently assure the safety or security of the code itself. Code signing certifies the source and integrity of the code, but it doesn't evaluate the quality or security of the code. The signed code could still contain bugs, vulnerabilities, or malicious code inserted by the original author. Signing ensures software is from the expected developer and in the state the developer intended. While code signing adds trust and authenticity to software distribution, it should not be relied upon to guarantee secure or bug-free code.
Description.
The first window is titled Bitwarden Installer 2022.10.1 Properties. Digital Signatures tab is selected. A section titled Signature List provides details of name of signer, digest application protections. Data exposure is a fault that allows privileged information such as a token, password, or personal data to be read without being subject to the appropriate access controls. Applications must only transmit such data between authenticated hosts using cryptography to protect the session. When incorporating encryption in code, it is important to use industry-standard encryption libraries that are proven to be strong, rather than internally developed ones. Error handling. A well-written application must be able to handle errors and exceptions gracefully. This means that the application performs in a controlled way when something unpredictable happens. An error or exception could be caused by invalid user input, a loss of network connectivity, another server or process failing, and so on. Ideally, the programmer will have written a structured exception handler, SEH, to dictate what the application should then do. Each procedure can have multiple exception handlers. Some handlers will deal with anticipated errors and exceptions. There should also be a catch-all handler that will deal with the unexpected. The main goal must be for the application not to fail in a way that allows the attacker to execute code or perform some sort of injection attack. One infamous example of a poorly written exception handler is the Apple GoTo bug, https://www wired.com/2014/02/goToFail. Another issue is that an application's interpreter may default to a standard handler and display default error messages when something goes wrong. These may reveal platform information and the inner workings of code to an attacker. It is better for an application to use custom error handlers so that the developer can choose the amount of information shown when an error is caused. Technically, an error is a condition that the process cannot recover from, such as the system running out of memory. An exception is a type of error that can be handled by a block of code without the process crashing. Note that exceptions are still described as generating error codes / messages, however. Memory management. Many arbitrary code attacks depend on the target application having faulty memory management procedures. This allows the attacker to execute their own code in the space marked out by the target application. There are known unsecure practices for memory management that should be avoided and checks for processing untrusted input, such as strings, to ensure that it cannot overwrite areas of memory. Client-side versus server-side validation. A web application, or any other client-server application, can be designed to perform code execution and input validation locally, on the client, or remotely on the server. An example of client-side execution is a document object model, DOM, script to render the page using dynamic elements from user input. Applications may use both techniques for different functions. The main issue with client-side validation is that the client will always be more vulnerable to some sort of malware interfering with the validation process. The main issue with server-side validation is that it can be time-consuming, as it may involve multiple transactions between the server and client. Consequently, client-side validation is usually restricted to informing the user that there is some sort of problem with the input before submitting it to the server. Even after passing client-side validation, the input will still undergo server-side validation before it can be posted, accepted. Relying on client-side validation only is poor programming practice. Application security in the cloud. Cloud hardening and application security are complementary capabilities designed to support the shared responsibility model in cloud environments where cloud service providers are responsible for securing the infrastructure and customers are responsible for securing their data and applications. Cloud hardening practices fortify the cloud infrastructure, reducing its attack surface, whereas application security ensures that software is designed, developed, and deployed securely. Together, these approaches create layered defenses that can counter many different types of threats. Cloud hardening includes least privilege access policies to restrict users to the minimum permissions needed to perform their duties. Encryption protects data in transit and at rest. Regular audits and continuous monitoring practices identify potential security risks, and regular vulnerability assessments and penetration testing detect and address any potential security issues or misconfigurations. Monitoring capabilities. Secure coding practices focus primarily on preventing software vulnerabilities, but also stress enhancements to logging and monitoring capabilities. These features support security analysts tasked with detecting potential threats and malicious activity in software. Writing code with enhanced monitoring capabilities improves the granularity and effectiveness of logging and alerting systems, which are crucial system monitoring tools. Implementing comprehensive and meaningful logging requires developers to ensure their applications generate logs that capture important events and activities to support security audits, incident response, and system troubleshooting. Secure coding practices encourage robust error handling to hide or mask sensitive debugging information, and this practice minimizes the risk of attackers exploiting information displayed in error messages. Integrating real-time alerting capabilities within the application code can significantly improve threat detection. For example, Code that triggers alerts when specific events occur, such as repeated failed login attempts or unusual data transfers, helps security analysts monitor applications more effectively. These alerts often indicate a potential security breach and provide crucial information for incident response teams. Rate your confidence. Software sandboxing. Sandboxing is a security mechanism used in software development and operation to isolate running processes from each other or prevent them from accessing the system they are running on. A sandbox is a protection feature designed to control a program so it runs with highly restrictive access. This containment strategy reduces the potential impact of malicious or malfunctioning software, making it effective for improving system security and stability and mitigating risks associated with software. A practical example of sandboxing is implemented in modern web browsers, like Google Chrome, which separates each tab and extension into distinct processes. If a website or browser extension in one browser tab attempts to run malicious code, it is confined within that tab sandbox. This action prevents malicious code from impacting the entire browser or underlying operating system. Similarly, if a tab crashes, it doesn't cause the whole browser to fail, improving reliability. Operating systems also utilize sandboxing to isolate applications. For example, iOS and Android use sandboxing to limit each application's actions. An app in a sandbox can access its own data and resources, but cannot access other app data or any non-essential system resources without explicit permission. This approach limits the damage caused by poorly written or malicious apps. Virtual machines, VMs, and containers like Docker offer another example of sandboxing at a larger scale. Each VM or container can run in isolation, separated from the host and each other. The others remain unaffected if one VM or container experiences a security breach or system failure. Sandboxing in security operations. Sandboxing tools are pivotal in security operations and analysis, particularly in detecting and understanding malware activities via forensic inspection. Sandboxing tools create an enclosed, controlled environment that allows the safe execution, also referred to as detonation, of potentially harmful software without jeopardizing the integrity of the IT environment. Examples of such tools include Cuckoo Sandbox, an open-source system that runs files within an isolated environment and scrutinizes their behavior, logging crucial activities like system calls and network traffic. Another important tool is Joe Sandbox, which does not require setup or installation in the organization's environment, but can be accessed via a web browser. Joe Sandbox leverages several analysis techniques, including machine learning, to examine software. Description. The Overview tab at the top is selected. The screen provides the Windows Analysis Report. A section titled Overview provides data on general information, detection, signatures, and classification. Two other sections are Titled Process Tree and Malware Threat Intel. Joe's Sandbox Analysis of a Malicious Executable File. Screenshot courtesy of Joe Security, LLC. You should be able to configure secure protocols for local network access and management, application services, and remote access and management. Guidelines for enhancing application security capabilities. Follow these guidelines when implementing network protocols. Assess the requirements for securing application protocols, such as the need for certificates or keys for authentication and TCP/UDP port usage. Deploy certificates to web servers to use with HTTPS. Deploy certificates to email servers to use with secure SMTP, POP3, and IMAP. Deploy certificates or host keys to file servers to use with FTPS or SFTP. Deploy certificates to email clients to use with S/MIME. Follow these guidelines for improving application development projects. Train developers on secure coding techniques to provide specific mitigation against attacks. Understand different categories of web application attacks that exploit vulnerable code. Identify injection attacks, XSS, SQL, XML, LDAP, that exploit the lack of input validation. Replay and request forgery attacks that exploit the lack of secure session management mechanisms. Review and test code using static and dynamic analysis, paying particular attention to input validation, output encoding, error handling, and data exposure. Rate your